Hey everyone, welcome back to today's lesson. Today, I will explore the fundamental concepts of quantum swarm optimization algorithm. So by the end of this tutorial, you'll be able to understand the algorithm and implement the algorithm using Python program. Please write comments in the comment section of this video tutorial. Also like, share, and subscribe. Let's go. The quantum-inspired optimization methods, such as the quantum cat swarm optimization algorithm, which are designed to harness the principles of quantum mechanics to enhance classical optimization algorithm. So the quantum cat swarm optimization is a variation of the cat swarm optimization algorithm that incorporates quantum principles. So to create a basic version of quantum cat swarm optimization in Python, you can follow this algorithm steps. The first one is define the problem. So you have to define the problems. What is the objective function that you wanna minimize or maximize? What are the constraints on the variation or solution? And then initialize the cat swarm. This can be done randomly or by using a heuristic method. Each cat should be represented by a position in the search space. Then the third step is update the cat position. So the cat position can be done using quantum cat swarm optimization algorithm. So this algorithm combines the cat swarm optimization algorithm with quantum mechanics to improve the accuracy and avoid local optima. And the fourth step is evaluate the objective function for each cat we defined here or initialized here. So we're going to the fifth step. So the fifth step is update the global best solutions. This is the position of the cat with the best objective function value or so far. Then we're going to repeat the steps 3, update the cat position, evaluate the objective function for each cat, and update the global best position, and repeat until the initialization or the termination or the terminate criterion is met. So this could be a maximum number of iterations, a certain accuracy threshold or a stagnation in the objective function value. Now we're going to implement the algorithms in Python. So to do this, first import NumPy and the function, define the function to optimize. So this you can replace this function with your own objective function. So let me define a fitness objective function to optimize that. This function takes x parameter and is going to return the sum of I square for every I in the iteration or in the X. X is a list of iterations. It's list of positions. So it's going to iterate and finally just sum up together and return the sum of that result. Okay. Now I'm going to define parameters. The parameters are, for example, the number of iterations. Let me define, for example, 100. It is up to you. Number of cards, how many number of cards? Here, 5, for example, and dimensions. The number of dimension, for example, 2, h bar, which is the value of h bar is 1.0 5 is actually initial value, 4, 5, 7, 1, 8, E, which is the power of 10 raised to minus 34. Okay, so once you define these parameters, we're going to understand what are the uses of these parameters in our optimization algorithm. So I will explain the usages of this algorithm step by step. So the first one is number of iterations. This parameter represents the number of iterations or optimization steps that the algorithm will perform, how many number of iterations can be performed. And in each iteration, the algorithm updates the position of the cards based on certain rules to improve the overall speed. Because based on the number of iterations, it's going to update the card position, evaluate the objective function for each card, update the global best position. So it's going to iterate from step 3 to step 5 until a termination criteria is met, which means until the number of iterations is greater than 100, okay? So the algorithm updates the position of the cards based on certain rules to improve the overall fitness. We're going to apply the quantum the quantum principles rules. And the second parameter is the number of cards. This parameter denotes the number of cards or agents in the swarm optimization algorithm. So in the context of cat swarm optimization algorithm, the cards represents the individual agents that are part of the optimization process. So each card's position in the search space is updated iteratively to find the optimal solution. And the third parameter is number of dimensions. So here, this is S. So this signifies the number of dimensions in the search space. In the context of optimization, especially in multidimensional optimization problems, the search space can have multiple dimensions that define the possible solutions. Each dimension represents a variable or a parameter that can be handled to optimize the objective function. Okay, and the last parameter is h bar. Basically, this parameter pronounced as h bar. In the context of provided code here, it's used as a scaling factor or a quantum-inspired constant. It serves as a fundamental constant in a quantum mechanics. So this is a constant, like other constants, for example, pi. Pi is a constant. Like that, this is a quantum constant, the fundamental constant in quantum mechanics, which is relating to the quantization of physical properties and is used to introduce quantum-inspired behavior into the optimization process. So its value is 1.0545718 times 10 raised to minus 34 meter square kilogram per second. Okay, now I'm going to initialize the position of the position of the cards. So cards here np dot random we just pass the number of cards and the number of dimensions. So here we just initialize the position of the cuts, and we also initialize the based noun positions and fitness values. So the based positions is cuts dot copy. We copy the cuts position initially defined here, and that is the best positions in the fitness. And we also find the best fitness. So NP dot array, we can fitness function. We call the fitness function we define here that's going to return the sum of the fitness. Fitness. Okay. Here we just pass C for every cut, which means in the cuts. Okay. So that would be aggressively select the best fitness. Okay, that's the function optimization. Okay, now so far so good, and now we are going to define the main optimization algorithm or loop, and for every in the range of this is elimination mechanism. We just don't need to use any value in this iteration, so I just ignore. But I used to iterate the optimization algorithm. So I'm going to implement optimization algorithm in the each iterations we defined here. 100 times of iteration can be performed in this algorithm. Iterations. For every I in the range of the number of cuts. In this number of iterations, I also iterate over each cut I have defined in the swarm. And now the next is quantum or quantum inspired update rule. So that is the base thing here in the iteration. We are going to update the quantum inspired update rule. So here, the position of the cat at the position of I is going to update that, and we use the sign function here. So I use h bar, which is a constant in the quantum mechanics, and multiplied by the cuts at position I. Okay, at position I. So it's going to update the cuts here, update the cuts position, and evaluate the objective of the function for each cut, and update the global based position here. And so now update the position. If the fitness improves. So the current fitness in this case is fitness function. I call that fitness function. And I pass cuts at position I. And if the current fitness, which is less than to the base fitness, at position I, Then the best position can be updated here. Best position is position I could be the cutters position I. So I am updating the best position, and the best fitness can be here based on that best position is here. So which means updating the global best position. Okay. And now the best fitness position I could be the current fitness, okay, in the iteration. So this iteration, these steps can be performed until the termination criteria is met. So it's going to iterate 100 times based on the number of iteration, and it's going to update the cuts position, that is here, the cuts position, and update the best position and best fitness position as well. Okay. So now we have finished implementing the algorithm. We are going to print the values. So this could be outside of the loop. For every, then we print the base positions and fitness values for every I in the range, in the range of the number of cards. We can print cards at position I, position the best position, we call the best positions at index I, and the fitness, so the best fitness at position I. Okay, now going to run this algorithm and see the output, the values of the best positions and fitness values together. Okay. Okay, here there is error. Sorry, this is what in the bracket, so I forget putting the brackets. That's why there is an error. And here there's also that is the type error. Best position is not defined here. Positions. I just put I here. That's why this is typo. So don't worry. Yeah, the cat at position 0 is the value, this one, the position, the best position is this one, the fitness 0, 0, positional, and so on. So this is what the algorithm of this, the quantum cat swarm optimization. So this algorithm basically demonstrates the quantum path optimization algorithm. So you can replace this function with your own function, and you can learn how to implement this algorithm classically. So this example basically integrated a basic quantum inspired updates rule using the sign function, using this sign function applied to the position of the cards here, the position of the cards. However, it is important to note that this example is a simplified version and doesn't fully capture the intricacies of true quantum cat swarm optimization. So, more advanced version of this would require a deeper understanding of both quantum computing principles and the cat swarm optimization algorithms. I strongly recommend that for a more complex implementation of quantum cat swarm optimization algorithm, you might need to refer to the recent research papers. Okay, because there is no framework that already implemented this algorithm. So this is what a classical example of quantum cat swarm optimization algorithm in Python program. So I hope this video was helpful. Don't forget to like, share, and subscribe, and also write your comments or thoughts in the comment section of this video tutorial. Thanks for watching today.